Hi, I will present the paper, A Unifying Framework for Characterizing and Computing Width Measures, which is joint work with Eduard Eiben, Robert Ganian, Thekla Hamm, and O-joung Kwon. Okay, so this work is all about width measures of graphs. And I want to start by giving some examples of width measures. So possibly the most famous one is Treewidth. And it can be illustrated like this. So you have some graph G, and then you build a decomposition of G where all these round things are vertex sets of G called bags, and they are arranged in a tree structure, as you can see. Now this decomposition has to satisfy certain properties. First, for every vertex in the graph, there is at least one bag containing that vertex. Second, for every edge, UV in the graph, there's at least one bag containing both the endpoints. And the third is that if you look at any vertex and all the bags that contain that vertex, then you have a tree in the decomposition. All right. So these three properties guarantee that if you remove a bag that disconnects the tree decomposition, then it also disconnects the graph. And this is very useful when you want to design algorithmic applications using these decompositions. All right, now the width of a tree decomposition is the maximum bag size -1, and the tree width of a graph is the minimum width of any of its tree decompositions. Now, I will talk about lots of width measures throughout this talk, and the second part is always sort of the same. So once you define like a width of some decomposition, then the width of a graph is always the minimum width of any of its decompositions of that type. And I will not repeat this over and over again. All right, so Treewidth is a very useful tool, but there's also a downside, which is that it is not very helpful when you consider dense graphs. So complete graphs already have a very large tree width, and therefore people considered a different graph variant, which is Clique-width, and that overcomes this problem. So I just want to give you an example of this definition. So Clique-width is originally defined in terms of some graph operations on labeled graphs, and these are the following. So first, you can introduce a new vertex with some label. So here we introduce vertex A labeled 1, and then you can keep on doing that. And one of the operations is also that you can take the disjoint union of two of these labeled graphs. So here we introduced another vertex B, and the label is 2. Okay, then there's an operator that connects all vertices of a given label with all vertices of another given label. Here we connect labels 1 and 2, so we put an edge between these two guys. All right, similarly, we can introduce another edge like this. Here we connect all vertices 2 with all vertices labeled 3. And then what we can also do is to relabel label classes. So here we have an operation where all the vertices labeled 3 will get labeled 2. Right? And then if we continue the construction like this, we see that we can get a C5. Okay, so that was just for an example. The width in this context is the number of labels that we use throughout this process. Right, so this is already very different from the definition of tree width, for example. Okay. Now, algorithmically, the way you use these width measures is always that you take this decomposition, which usually has a tree-like structure, and you do some type of dynamic programming over this tree structure. And then very often you get algorithms that are polynomial time if the width is constant. Okay, so there are many, many width measures. This is just an overview of the few of them. And the focus in this talk is that we want to group these measures according to their expressive power, and we will not care about specific values of the width. We just want to know if they're asymptotically the same or not. So what does that mean? So we say that some width measure W1 asymptotically dominates another width measure W2. Basically, if there are more graphs, like if there are more graphs of bounded width for W1 than for W2, or in particular, if the width W2 is bounded, then width W1 should also be bounded. For example, Clique-width dominates Treewidth because, well, every graph of bounded Treewidth has bounded Clique-width, but not the other way around. Okay, so this is what we say. So we would say that Clique-width asymptotically dominates Treewidth. Okay, and we say that two width measures are asymptotically equivalent if they dominate each other. So now if you look at this picture, then, well, first of all, the width measures that are on top dominate the ones that are below. And if two width measures are in the same group, then they are actually asymptotically equivalent. Okay, so many of these width measures are probably known to people, but there is one up here that I want to motivate a little bit, which is mim width, which is not so famous, I would say. Okay, so as you can see, it's very high up in the hierarchy, at least in this picture. So it has very high expressive power. And you can see that by the fact that many well-studied graph classes actually have constant mim width. So if you look at all of these graph classes here, their mim width is bounded by some constant. And it's interesting to note that even interval graphs and bipartite permutation graphs down here already contain graphs of unbounded Clique-width. Okay, so in terms of algorithmic applications, well, if you have a bounded mim-width decomposition of your graph, you can solve many types of problems, in particular independent set, dominating set, and several variants, and also partitioning problems like age homomorphism. And furthermore, you can solve problems that require some kind of connectivity of the solution, like connected dominating set or connected vertex cover, and problems asking for acyclicity constraints like feedback vertex set. And there are lots of other problems. So just want to make the point that there are many algorithmic applications for mim width if you're given a decomposition. So it's still an open problem how to approximate mim width in general. All right, so let's go back to this this picture. So we saw that there are many width measures, and at the beginning in the introduction we saw that, well, there's Treewidth, there's Clique-width, they're both width measures, but the definitions don't seem to have a lot in common, right? So you might ask yourself, what does width even mean in this context? So why do we call these graph invariants width? While some others, we don't call them width, right? So you could say, well, this is just the way things have been defined, or you could search for unifying theories, like unifying explanations that width measures have in common, right? And this is what we've been doing in this paper. Okay, so if you want to unify width measures, there are two things that you have to take care of. Well, first you have to unify the way that you define the decomposition. And there is one way that that is very commonly used, and I think that it is very nice, that it has a very nice motivation in terms of algorithmic applications of width measures, which I want to show you now. So the idea is that you take your graph G and then you recursively decompose it into smaller parts until you have single vertices basically. And then, like you would do in some sort of divide and conquer algorithm, you go back up and you combine the solutions when you're doing an algorithm on this decomposition. And in this context, of course, it is very crucial what is the complexity of those cuts that you encounter, right? So if you have a solution for one side and a solution for the other side, and you want to find a solution for their join, sort of, then it's of course very important how complicated their interaction is. Right, and in this type of decomposition, you always measure the width as the complexity of these cuts that appear during the decomposition process. Okay, so how do you model this more concretely? So you do like this. So this process is modeled by what we call a branch decomposition, where you have a tree of maximum degree 3, such that the leaves of the tree correspond to the vertices of the original graph. So here we have a branch decomposition of this example graph. Right, and then each of the edges in this decomposition corresponds to a cut that you would encounter in this decomposition process. Right, because if you take one edge and you remove it, then you have two connected subgraphs of this decomposition, and you can just look at where the vertices, to which leaves the vertices are mapped, and that you naturally have a cut associated with each edge of this decomposition. Okay, so let's look at some width measures that are defined using these branch decompositions. One is maximum matching width, which, as the name already suggests, it just counts the size, the maximum size of any matching that goes across the cut. And you can actually show that this is asymptotically equivalent to Treewidth. Okay, so for example, if we look at this edge here, we have CF on one side and ABDE on the other side. And the bipartite subgraph that goes across looks like this. Okay, and here we have a matching of size 2, right? So the width of this cut would be 2. Now there's only one cut where the width could possibly be bigger, which is when we have 3 vertices on each side. But we see that here also the maximum size of any matching is 2. And right. So now the width of this decomposition will be the maximum width of any cut. And so the width of this decomposition, the maximum matching width of this decomposition is 2. Okay, so let's look at another width measure called rank width, which is the GF2 rank of, which is computed as the GF2 rank of the binary adjacency matrix of the cut. So I adjusted the graph slightly so that the example becomes more interesting. So let's look at it again at the same cuts. So if we look at this cut, then we see, then again, we take the vertices CF on one side, ABDE on the other side, and then the binary adjacency matrix looks like this. And this matrix actually has rank 1, okay? And if we look at the other cut, then the matrix looks like this, and this matrix has rank 2 because we can see that the first row plus the second row gives you the third. Okay, so this decomposition will have rank width 2. And also, so for rank width, it has been shown that it is actually equivalent to, asymptotically equivalent to Clique-width. All right, so for both these width measures, we have characterizations in terms of branch decompositions. But you could also see that the way that the complexity of the cut is measured was very different in these two examples. Which is why we now go to step 2. So we want, in our framework, we also want to unify the way that we measure the complexity of these cuts. Right, and this is how we arrive at this definition of F branch width. So the idea is that we take some family of bipartite graphs F, and now the complexity of a cut is just the size of the largest member in F that appears as an induced subgraph across the cut. Right, and okay, so here I cheated a little bit. I just said it's the size of F, but I didn't really say what that means. So what we're actually interested in is the number of vertices that you have on one side of the cut. And the reason is that, well, the width of the cut should really depend on how many vertices on one side are involved in the size of the biggest obstruction, rather than what the obstruction looks like, right? Because, well, you might say maybe it's more natural to take the number of edges in F, but this is not really the case because of what I just said. All right, but now, since we're considering only the vertices on one side of the cut, we require some kind of symmetry constraint. And first of all, we only want to allow bipartite graphs that have equally sized sides. Sorry, this is a typo here. Okay. Another thing that you might think of is that it's quite unnatural to skip width values, right? So I mean, if you have some family of bipartite graphs where you can obtain width 2, 3, and 5, say, but you cannot obtain width 4, then this doesn't really make sense if you think about what a width measure is actually supposed to do, right? So ideally, you should have like at least one graph that witnesses that your width is some k for any k. And second of all, if you look at the structure of a graph in F that witnesses that your decomposition has width k, then it might also be natural to require that it should say something about the structure of the graphs that witness width strictly less than k, right? That they're somehow related and not just sort of a random set of graphs, because that would not really tell you very much, in particular if you want to design algorithms using these types of decompositions, right? So this led us to the following requirement, that we say that the graph class F should be what we say a partner hereditary. So what does this mean? So first we fix some bipartition of, so given a graph in F, we fix a bipartition of the two sides, and we sort of partner up every vertex on the A side with some vertex on the B side, right? So here you would just partner them up by indices. So A1 is partnered up with B1, A2 with B2, etc., etc. Right? And then what we require is that if you take any subset of the numbers of 1 to n, then the subgraph of F that is induced by the partners with that index is again a member of F. Okay, so let me show you some examples to clarify this. So first of all, we can see here again that partners mean there doesn't have to be an edge between two partners. It just means that they sort of have the same index, right? Okay, so here we have these three families, and the first one we can see is actually not partner hereditary. And well, why is that? So say you take the numbers from 2 to n as your index set I, then they induce an empty bipartite graph, right? But this one is not contained in F1 because we always have this one vertex on the left that sees everybody on the right. Okay, so F1 does not have this property. On the other hand, we can observe that F2 does have this property. So this is the class of all matchings. And if we take any subset of the numbers from 1 to n here, then again, we will get a matching induced by these guys, just of a smaller size. Okay, so this class is actually partner hereditary. And we can also see that if we take F1 and we put like this class of empty bipartite graphs, or like edgeless ones, into this class, then again, we get something that is partner hereditary. And why is that? Well, I mean, any subset here in F1, either it contains the vertex A1, in which case, again, we just have a smaller graph that looks like this, or it doesn't contain A1, in which case we have an edgeless bipartite graph. Okay. So now what does this capture? So we can see that asymptotically, so if we take F to be the class of matchings, anti-matchings, balanced chains, and complete bipartite graphs, then the corresponding F branch width is asymptotically equivalent to Treewidth. If we take the same graphs, but we remove the complete bipartite ones in F, then we actually obtain something that is equivalent to Clique-width. And I think this is already quite interesting, right? Because we saw that the initial definition of Treewidth and Clique-width is, these definitions are quite different. But we see that in this picture, the only difference it makes is to include the class of complete bipartite graphs as a part of the function measuring the complexity of the cuts or not. Okay, and finally, mim-width is actually defined this way. Okay, so for mim-width, you just take the class of matchings and yeah. Okay. So, okay, so this is quite nice, but maybe it is not so surprising, right? Because, well, this condition of being partner hereditary is not too strong. There are many possible ways of coming up with a partner hereditary graph class. And so you might say, well, there are so many choices, so surely some of them will capture these width measures, right? Okay, but we can take this a little bit further and make this whole framework much more tractable. So for that, we introduce the notion of size identifiable families, and we say that a partner hereditary graph family is size identifiable if for all n, there is precisely one graph with 2 n vertices in F. Right, in other words, for every n, there's precisely one graph that witnesses width n. Okay, and now what we managed to show is the following. So if you take any partner hereditary graph family and then you restrict it to the union of all size identifiable graph families that are contained in F, except for some constantly many exceptions, then you obtain 2 equivalent, asymptotically equivalent F branch width parameters. Okay, so this up to constantly many exceptions is just a technical condition that we have to put that, yeah, is not so important. So basically it says that we can always restrict ourselves to these size identifiable families that are contained in F if we want to asymptotically compute F branch width. All right, but now you might ask, well, how many size identifiable families do we actually have? And now we managed to show that there are only 6 such families. Okay, so this is already much, much smaller than, well, you know, infinitely many. And these 6 size identifiable partner hereditary graph families are those. So we have the edgeless graphs, the matchings, the balanced chains, and their bipartite complements, which means the complete one, the anti-matchings, and the scoop chains. Okay. Now, so just to, if you got lost a little bit, I just want to give a recap of this whole story. So we have many width measures, and we're trying to figure out if there's a unifying way of characterizing them. Then in step 1, we unified the decomposition method and we chose branch decompositions. In step 2, we were unifying the cut functions and we came up with this notion of F branch width for partner hereditary graph families F. And we saw that this already captures all of these width measures. Right, and then we took it one step further and saw that actually only 6 partner hereditary graph classes truly matter if you consider width measures in this asymptotic context. So if you don't care about the precise value, you just care if a width measure is bounded or not. Okay. Now, so far we only cared about characterizing width measures using this f branch width, but we can also use f branch width algorithmically. So in particular, if we know how to approximate f branch width, then we also approximate all these width measures that we showed the asymptotic equivalence to. So yeah, so this is something that is useful for algorithms. So let's once more look at this picture. So here we said we only have to care about 6 partner hereditary graph classes, and we can show that you can actually bring this down to 3 graph classes. Okay, and these 3 graph families are what we call the primal ones, and they consist of the matchings, the anti-matchings, and the chains. Okay, so if you can give an algorithm that computes the f branch width for any combination of these 3 graph families, then you can approximate any possible f branch width. And yes, so you can always restrict yourself to these what we call primal graph families. And now what we did is that we showed several cases in which we can approximate all the f branch width parameters by showing that for any union f star of primal graph families, we can, the problem of computing f star branch width has a number of algorithms that are efficient when your graph has other structural restrictions. So for example, this problem is fixed parameter tractable if we consider as a parameter the tree width plus the maximum degree of the graph. It is also fixed parameter tractable parameterized by the tree depth of the graph, and it has a linear kernel parameterized by the feedback edge set number of G. And as a consequence, we have also that we can compute the MIM width under any of these structural parameterizations exactly. And now maybe you think that this is not so satisfying, because of course the goal would be to compute f star branch width itself, right? Like f star branch width parameterized by f star branch width. But we expect that you require quite some heavy machinery for this because, well, first of all, it contains the problem of computing MIM width as a small special case. And this has been open for several years now. And yeah, I mean, like I said in the beginning, there's really not much known about computing MIM width. So these results can also be seen as a step of a better understanding of how we can obtain algorithms to compute MIM width. All right. So as a conclusion, I want to show you this picture again. So we had this unifying framework to characterize width measures. And we found that there are only very few graph classes that we have to consider in this context when defining this width measure. And we saw that on graphs of low tree width and maximum degree, or tree depth, or feedback edge set number, we can approximate any f branch width efficiently. Now for future problems, of course, it would be great if we manage to show how to approximate any f branch width efficiently parameterized by the target width. For a more modest goal, I think already here in this parameterization for tree width plus maximum degree, it would be nice to get rid of the maximum degree. And finally, so we now have this new framework, and there are actually some new width measures that can be defined in this framework that have not been considered before, and it would be nice to see what kind of algorithmic applications we can have of those width measures. All right, that's it. Thank you for your attention.